in today's video lecture, I shall be discussing about the new topic in compiler design, that is intermediate code generation. As you are already aware that intermediate code generation is one of the phase of the compiler design. Okay, so before moving on to this particular topic and the details about this particular topic, let's brush up the topics that were covered in last two video lectures. Okay, if you remember, we had discussed about the first topic after the winter break. The first topic that we had discussed was syntax directed translation. Okay, so a new type of grammar, a new form of grammar known as an attribute grammar was devised in the year 1981 by Donald Knuth. Okay, so the main reason for him defining this attribute grammar was to define the attributes for the production of the formal grammar, thereby associating the attribute with its value. Okay, so in context free grammar, what we had is we would define the grammar using the quadruples. Okay, and in addition to this particular definition, so we had set of production rules. Okay, so this particular set of production rules were in terms of the variables and the terminals. However, this particular set of rules did not have any values associated with it, neither it had any semantic associated with it. Okay, so the set of rules would be given, and based on the set of rules we would evaluate a particular expression, generate a parse tree. However, we were not aware of what those set of rules specifically implies, or what we are supposed to do whenever we encounter those set of rules. We were only substituting the particular variable nodes into the sub nodes, whatever this set of rules would imply to us. Okay, however they felt the need of coming across or coming up with certain what you call semantics that would be associated with those set of rules that would give the attribute certain value and certain meaning. Okay, that is how the attribute grammar came into picture. Okay, and one of the what you call the one of the technique, or one of the translation mechanism those attribute grammar came up with was a syntax directed translation. Okay, it had a grammar, it had the rules, it had the semantic that is associated with it. Okay, so we have already discussed this two examples wherein we do not just have the set of rules, okay, but we also have the semantic associated with each of the production rules that is given in this attribute grammar. Okay, and this mechanism is known as syntax directed translation. So based on this particular syntax directed translation, we can even evaluate this particular grammar, evaluate this particular string, for the grammar which is given. Okay, so we have taken this example and we have tried evaluating it and generating the output. We have also discussed about the attributes in the syntax directed translation are basically categorized into two. One is the synthesized attribute and another is the inherited attribute. Okay, so before moving on to the differences between these two, we had seen that a particular example like A tends to BCD, where BCD were children, A was a parent node. Okay, and suppose if the parent is taking the values from its children, we call that mechanism as synthesizing. Okay, so such attributes are known as synthesized attribute or S attribute. Okay, however, if the children inherits the value from the parents, we call it inheriting or the mechanism as inheritance. Okay, or inheriting properties. Okay, and apart from children inheriting the properties or the values from the parent, it can even inherit the property from its sibling. However, the constraint that has been applied onto this particular inheritance is only the leftmost sibling's value could be inherited. Okay, so if a parent is extracting the value from the children, we call it those kind of attribute, we call it as synthesized attribute or S attribute. And if the children is extracting the value from the parents, so those kind of parents or its leftmost sibling or the left sibling, okay, which is given in the format, okay, as per the format. Okay, so that particular kind of attribute we call it as inheriting attribute or L attribute. Okay, so and based on this particular definition, we had seen how S attributed SDT differs from that of L attributed SDT. Okay, you can just go through it because we have already discussed in the last class. Okay, apart from that, the next topic that we have discussed in the last two videos were the symbol table. Okay, we are already familiar with what a symbol table is. However, we did not know about the details of the symbol table until and unless we discuss about it in the last class. Okay, but you need to remember, the only thing that you need to remember is symbol table is nothing but a simplified table, or we call it as a data structure, okay, that is used by the compiler or interpreter at every phase as a reference table. Okay, and the symbol table has several uses, and it is used basically by all the phases of the compiler. Okay, if you remember in the last class, I have discussed how the analysis phase use the symbol table, how the synthesis phase use the symbol table, and within the analysis and the synthesis phase, what are the different sub phases that makes use of the symbol table. Okay, and we have also listed and discussed about the different operations that can be performed in the symbol table. Though the list of operations are operation is quite long. These are the list, the one which is given in the presentation are the major operation. Okay, if I want to insert a value or a symbol into the symbol table, I would use insert operation. If I want to find a symbol into from a symbol table, I would use a lookup operation. If I want to remove a particular symbol from the symbol table, I would use delete, remove symbol, or pop, depending upon the type of compiler that I am using. If I want to free the symbol table, the entire symbol table or only a specific symbol table, okay, and I would be using the operation called free. And if I would like to allocate a new entry into a symbol table, or new symbol table, or a new local symbol table, then I would use the operation called allocate. Okay, now, and here we had discussed everything in detail, and then later we had discussed also about the scope management, where we had discussed about the global symbol table and local symbol table. Okay, so it's like a local variable and a global variable in the other programming languages that we have already dealt with in the last few semesters. Okay, so local symbol table, the symbols and its relevant information that are present in the local symbol table can be used by procedure only within the scope. Okay, that's the reason why this local symbol table is also known as scope symbol table. However, the symbols that are present in the global symbol table can be used by all the procedure, okay, throughout. Okay, that's why it's known as that's why the symbol are known as a global symbol, or that particular table is known as the global symbol table. Okay, so these are the two important types of symbol table, and in order to determine the scope of the symbol, okay, depending upon where it is present in the scenario, the symbol table are generally arranged in the form of a hierarchical or a tree structure. Okay, I have taken this example, and this is the hierarchical structure that I had presented. Okay, so now moving on to the next phase of the compiler. Okay, so in between the analysis and the synthesis phase of the compiler, so we have a phase that is known as intermediate code generation. Okay, so once so the front end analysis analyzes the front end of the compiler, so analyzes the source code and creates an intermediate representation. Okay, so intermediate representation is created via a phase of a compiler which is known as intermediate code generation. Okay, so and the intermediate code generation phase generates the output, that is IR, and gives it to the back end of the compiler. Okay, and the back end of the compiler comprises of code optimization phase and the target code generation phase. Okay, so we can also say, here I have highlighted in the as a note, the details of the source code are confined basically to the front end of the compiler, whereas the details of the target code are confined to the back end of the compiler. Okay, and this and we know that the compiler basically comprises of several phases, but it's broadly divided into analysis and the synthesis phase. Okay, so the front end analyzes the source code. okay, generates the intermediate code. That intermediate code is given to the back end of the compiler, which comprises of the phases like code optimization and code generation. Okay, now what happens with that intermediate code? Okay, those intermediate code or the representation that is generated by the intermediate code generation phase, we call it as IR, that is intermediate representation. Okay, and the intermediate code can be represented either in the form of a parse tree. So we have already dealt with what is a parse tree, or we also call it as a syntax tree. Now we'll come across a new form of tree, that is a directed acyclic graph. Okay, so we also call it as DAG. Okay, so the intermediate code or the IR, the intermediate representation that is generated by the intermediate code generation phase, okay, can be either represented in a form of a parse tree or a syntax tree, or it can be represented in a form of a directed acyclic graph. Okay, for any kind of expression that is provided. However, the choice and the design varies from compiler to the compiler. Okay, now as I've already told you before too, okay, so the different, as we were talking about the different operation that can be performed on a symbol table. So we had said that lookup operation is the name of the operation that is given in one compiler. However, in some other compiler, this lookup operation is also known as search symbol. Okay, though the meaning of the semantic of the operation is same. Lookup also, it's to search for a particular symbol, and search symbol is also to find a particular symbol in the symbol table. However, the terminology or the nomenclature is slightly different. Okay, similarly, the intermediate representation, okay, or the IR, if it has to be represented, okay, some of the compiler uses a parse tree or a syntax tree to represent it, okay, whereas some of the compiler even uses directed acyclic graph, okay, to represent it. Okay, however, it could be represented in any form depending upon how the compiler has been designed or programmed. Okay, now moving on to the next subtopic in this intermediate code generation is the three address code. Okay, so three address code can be considered to be as one of the method. Okay, there are several methods, however it is considered to be one of the method to represent the intermediate code. Okay, three address code is one of the most popular method from among the list of methods that are available in order to represent the intermediate code, because okay, the main reason is it is basically built upon two important or two basic components. First is the addresses, the second is the instruction. Okay, now when I talk about an addresses, it could be one of the following. Address could be one of the following, that is, it could be a name, it could be a constant, or a compiler generated temporary variable. Okay, so when we talk about address, okay, it could be a name or a constant or a compiler generated temporary variables. Okay, so please remember this particular temporary variable, because whenever we represent intermediate code using this particular mechanism, that is three address code, we have to use the temporary variable. We cannot use the normal expression that we use in the other scenario or the other situation. Okay, so when given a particular statement or a particular expression, okay, there are two things that we have to perform. Okay, if I want to represent it using a three address code. Okay, first thing that you need to remember is translation of a statement or an expression to its intermediate form. First is using three address code. Okay, that is, suppose an expression or a statement is given, so I need to translate that particular expression or a statement to its intermediate form using one of the mechanism, and here we are using a three address code mechanism. Okay, second is further representation of the data structure of the intermediate representation that is generated using three address code is using quadruple, triples and indirect triples. Okay, so what does it mean? Okay, when a statement or an expression is given, okay, so whenever we have we have to represent the intermediate code, okay, and a statement or an expression is given, so I'll be using one of the method to represent the intermediate code. So I would translate those statement or an expression using a three address code mechanism. However, okay, now if I want to represent the data structure of the intermediate representation, okay, if I have the expression is converted into three address code. Now if I want to represent the data structure of the intermediate representation that has been generated using 3 address code, I would use 3 different techniques. Okay, the first technique is a quadruple, triples and indirect triple. Okay, now this quadruple, triples and indirect triples are the methods, or what you call the techniques, that is used to represent the data structure of the intermediate code that has been generated using a 3 address code. Okay, data structure representation is used using quadruple, triples and indirect triples. However, the intermediate representation is representation of that particular expression can be translated using 3 address code.